Welcome to day 13. Your homework for the final time is to work on the area function packet that will be collected tomorrow at the start of class. It will be graded like a problem set, so it will be graded for correctness. And we're going to work on today the AP problems. So if you can flip in your blue notes packet to the AP problems. And we're going to pause for 1 minute to let you read the question and see if you can start thinking about how to approach it. Okay, for part A. And you're probably going to want, I should mention too, you're probably going to want your notebooks out for this. There's not going to be enough space, most likely, to do all the work that we need to do just on the bottom of the page. So we'll pause for a minute. If you could take your notebooks out, read through the question, and see if you know how to start approaching part A, and then we'll talk about it together. Okay, so we want to see how many gallons of sewer have entered. So in other words, we want to see how much sewer has accumulated. And we've been working with accumulation functions. Normally, we would have to consider if it's starting anywhere, but we're not. We're starting with an empty treatment tank. And in reality, all we care about is what's entering. So I actually take that back. Even if it started at a certain level, we would just want to know how much is actually entered, so the changed amount. So we need to work with an integral. Again, this is part A. We're starting at time 0, and we're going to time 4. And our entering rate of change is the E of t there. So that's just 850 plus 715 cos of pi t squared over 9 dt. So this is an expression, or an integral, that can be put in the calculator now, and we can just round it to the nearest gallon. So we're going to pause for a minute for you to punch that in, round where you need to round it. Make sure you are in radian mode, and remember, on a calculator page, the template for this is next to the 9. So we're going to pause for a minute and give you a chance to put that in. Make sure to round where they want you to round to. So we should have gotten to the nearest gallon, 3,981 gallons. Okay, just so you can get a visual of what we just did there, here's the graph of our rate of change for the entering of sewage. We did 0 to 4. That's a poorly drawn line. But basically, from 0 up to that line, we found the area that is under the graph. And we found that that was approximately 3,981. So that is the accumulated sewage over the first 4 minutes. All right, next part, part B. So for our time frame from 0 to 4, we want to know at what time was the amount of sewage in the tank greatest. And then we want to know to the nearest gallon, what is that maximum amount of sewage? So, to find out when the amount of sewage in the tank is the greatest, we need to take into account 3 things. We needed to take into account how much sewage started in the tank, which in this case, underlined in red there, was that it started with 0. We need to take into account the rate at which it is entering, and we need to take into account the rate at which it is leaving. So we are going to define a function for the amount of sewage that is in the tank. So we're going to call it A of t. When you have your accumulation function and you're writing that amount, we always want to consider what's been already in there. So we don't have to write this, but just so we get in the habit, I'm going to write 0 plus here. Just so we're clear that, all right, it actually started with 0, because it's not always going to start with 0. And then we're going to do an integral for the amount that is entering and leaving, because those were given as rates. So we're going to do from 0 to 4. We'll have our 850 plus 715 cos of pi t squared over 9. That's the rate that we're entering. And then we also have to take into account the rate that we're leaving, which is a constant 645. So we'll do minus 645, and then we'll have our dt on the end. Okay, now we could have if we wanted, because we actually already know that first part of the integral. We have that from before. So we could have written that value out, but you would have wanted to, you would have had to keep it out as the exact form, which would be problematic, because you would have to somehow express it all the way. So I would suggest to actually write out the function like we did here, even though we know the value of what it is from above. Now the other reason we would want to write it out is because, oops, and actually I made a mistake. We want to not put 4 here. We want this to be t because we don't know where it has happened yet. And because that's going to be t, we would want this to be x, because it's got to be some different variable. Now the reason we're keeping t in the problem is so that when we actually do our derivative, it will be in terms of t. All right, so we want a maximum amount. We want the greatest amount. So we know to work with maximums, you should take a derivative. So we'll do a prime of t. Derivative of a constant is just 0. And this is now our second fundamental theorem of calculus. The derivative of this integral, when we're going from a constant to a variable, we're just subbing that in. So this is really just 850 plus 715 cos pi t squared over 9 minus 645. So that's our derivative. After we find a derivative, we always want to find our critical values, because in reality, we already know our interval. Normally, we would find our interval even before the derivative, but we've got an equation, we've got an interval, we've got our derivative. Now our critical values, we're going to set this equal to 0. Now I'm just going to combine our like terms there, the 850 and the minus 645. So really that's just going to give us 205 plus 715 cos pi t squared over 9 minus 645. And what we're going to do is we're going to give you a second to graphically find what these zeros are of this function. Now remember, we only care about zeros that are between 0 and 4 on our interval. So we're going to pause the video for 1 minute and see if you can find what those zeros would be. Oh, keep in mind, when you do them graphically, you would have to put an X instead of T on the graphs page. Okay, so when we put that in on the graphs page, we should have gotten t equals 2.309 and t equals 3.559. There's the picture of the graph right there. Okay, so that should have been what you got. And remember, we only, even though there's one at about 4 point something, we only cared about 0 to 4. So we're going to make our number line now, because our last thing we have to do is our tests. Our interval was 0 to 4. We have our 2.309 and 3.559. Now, our labels here, you can just write it as a prime of t and t. But for our test numbers, what's nice is we can just look at the graph. We don't have to actually punch in the equation. Well, from 0 to 2.309, we've got this derivative graph. Notice it's above the x-axis, so we know it's positive. In between the 2.3 and 3.5 numbers, it's below, so it's negative. and then afterwards it's back to positive. So we can use the graph to actually help us find those test values. Now, we wanted to know when it's the greatest. We have a relative max at t equals 2.309 since a prime of t switches from positive to negative. Well, you might have noticed our interval that we had at the beginning was a closed interval. When you have a closed interval, you've got to check the endpoints and any relatives. So we're checking in our accumulated amount. So we've got to check a of 0. We've got to check a of 2.309. And we also have to check a of 4. Now, it is enough for notation to just have those written, but keep in mind what we're filling that into. You are now on a calculator page, going to type that in. A of 0, we shouldn't need to type in. 0 plus an integral from 0 to 0 should just be 0, or you can think of it as at time 0 we had nothing. We just have to do the 2.309 and the 4. So on a calculator page, you're going to type in our a of t function, but fill in for t the 2.309, see what you get. Fill in the 4, see what you get. And just notice as you're doing that, they're going to want that sewage amount to the nearest gallon. So we're going to pause the video for 2 minutes, see if you can find each of those to the nearest gallon. Okay, for the 2.309, we should have gotten 1,637 gallons. I guess we should throw gallons on the 0. And we should have gotten 1,401 gallons there. So the final thing, we'll just make sure we answer the question. We wanted to know what time t is the amount of sewage the greatest, and what is the maximum amount of sewage in the tank. So we can say maximum amount of sewage is 1,637 gallons and occurs at 2.309, whatever our time units were, hours it looks like. Okay, so that summary statement would be our final statement. I would just suggest always reread that question and make sure you've actually answered it before you move on to the next part. And the third part of this one, part C. So the cost of treating raw sewage that enters the tank at time t is that expression there, dollars per gallon to the nearest dollar. What is the total cost of treating the sewage that enters the tank during the time interval? Notice we only treat the stuff that enters the tank. And we're doing it from 0 to 4. So we are just going to take our entering expression, which we used in part A, and then we have to, and that's going to give us the gallons that are coming in. Well, we need to multiply it by the cost per gallon. So we'll multiply it by 0.15 minus 0.02 t. And then, oops, I have, nope, that's good for parentheses. I don't need that last one. And we'll just have a dt at the end. So take a second and punch this in. Notice it says we want to the nearest dollar for that. So we'll pause 1 minute to allow you to get that answer. All right, so we should have gotten 474.32, so to the nearest dollar, $474. So there's one of these types of questions on every single AP exam. It's always on the calculator section. It's always really, really similar. So doing these now, you notice already encompasses what we've learned this year. It encompasses our integrals, which we're doing now, but then it also deals with the optimization that we did last unit. And so one of these you'll see definitely on the AP. So we're going to try another one. If we flip to the next page, we're going to pause the video for about 4 minutes or so. I want you to read the question and then see if you can do part A on your own. Okay, and then we'll talk about what part A should look like, and we'll do parts B and C as a group. Again, you probably want to put it in your notebooks. You won't have enough room, most likely, on the page. Okay, similar idea. We've got one equation for stuff entering, another equation for stuff leaving. So the piecewise one there, the horizontal lines is the leaving. The entering is the curved one. So we want to know how many gallons of water entered the tank on our interval 0 to 7. So for part A, we're just going to have an integral from 0 to 7. We'll have our entering equation, 100t squared sine radical t dt. And we should just punch that in. We get 8263.80. They told us we wanted to round to the nearest gallon. So the nearest gallon, 8,264 gallons. Okay, very, very similar to the first one that we saw on the previous page. You'll find that a lot of times the first question for the accumulation one is something like this. You just simply set up an integral based on what they told you and calculate a value. All right, part B. Find the time intervals during which the amount of water in the tank is decreasing. Well, if the amount of the water is decreasing, we want to look and see when is the water leaving the tank greater than the water that is entering the tank. So basically we're looking where are the horizontal lines above the curve. Now they told us what those intersection values were for t right here, which that was quite convenient. So our interval should be from 0 to 1.617. And again from from 3, because we're starting right here, to the intersection point of 5.067, or 76, sorry. Now we have to give a reason. Well, we were able to determine this because the leaving rate was greater than the entering rate. So we can simply say that f of t, which they told us here was the entering rate, was less than g of t. Okay, so we can even, maybe we'll write since in there too. So those are our intervals, since f of t was less than g of t on those intervals. Alrighty, in part C, at what time t is the amount of water in the tank the greatest? To the nearest gallon, compute the amount of water at this time. Should seem really familiar, this question. Very similar to what we did on the last one. So we know when we're doing an optimization, we've got to start with an equation. So for our equation, we'll stick with A for like the accumulated amount again. So we'll have A of t equals, we always want to begin with where are we starting at our initial time. Well, our initial time is 0, and this time they told us there was 5,000 gallons in the tank. So we've got to start with 5,000 plus, and then we're going to have our integral, and we'll have the incoming amount minus the outgoing amount. Now, because this is a piecewise function and it changes, we are just going to represent those in function notation, which is perfectly fine. Now, notice here we had started at time 0, and we want to finish at time t. Because we have t on the integral, we got to make sure we use a different variable inside the integral. So in here, we're going to have our entering amount. So we'll call it f of x. X, they often refer to that in math as a dummy variable. Okay, we're just picking some variable so that it'll get replaced with the t. And then minus g of x dx. So that's our equation. They already told us our interval, so we're good with that. Next, we would need the derivative. So a prime of t, well, the derivative of 5,000, that goes away. And do the derivative of the integral, we're just subbing in t for the x's. So we're going to have f of t minus g of t. Well, next we want our critical values. So we want to know when f of t minus g of t equals 0, or in other words, we want to know when g of t is equal to f of t. Well, they already told us that in the question. That would be when t was equal to the 1.617 and when t was equal to the 5.076. So we can do our tests. Our interval went from 0 to 7. We've got each of those critical values. Now keep in mind, on your number line, you also have to put where it doesn't exist. So we had an open circle spot there. Okay, so we have to park that 3 on there as well. All right, so we still have to label. We've got t here, and this was a prime of t. So, looking at our graph, the entering amount is less than the leaving amount in the first part. Then the entering amount is greater from the intersection till 3. Then it's back to the entering amount be less, and then the entering amount is greater. So we're looking for when it's the greatest. So we've got a relative max at t equals 3. So we would say t equals 3 is a relative max since a prime of t switches from positive to negative. Well, keep in mind we had a closed interval, so we have to check our endpoints as well as that relative that we just found. Well, we know from the initial information that this was 5,000 gallons at a of 0. That was our starting amount. But we have to do 3 and 7 in our a of t amount. So remember, that includes the initial 5,000, then plus our integral. Now, when you are doing it for 3, keep in mind that we're at 250 for the g of x when we're going from 0 to 3. So maybe we'll write that out down here. So for a of 3, we'll have our 5,000 plus, we're going from 0 to 3. We'll have the 100 t squared sine square root of t. That was our entering expression. And then if we're on 0 to 3, the leaving was 250. And then we got dt. So that's going to give us our a of 3. And we'll have you calculate that in a second. But let's set up our a of 7 one. So for a of 7, we're going to have 5,000 plus, and then I'm going to leave a blank here, because this is going to be whatever our answer was as the a of 3. Because we have to break up the integral separately, since from 3 to 7, the rate that it's leaving switches. So again, in this blank here, you'll put whatever your answer is that you got for a of 3. This will then be 100 t squared sine square root of t minus 2,000 now in this case. And we'll see what that gives us. So we're going to pause the video for 3 minutes, sub in your a of 3, see what you get. Then put that in the middle, put in for a of 7, see what you get, and then we'll come back and we'll make a concluding statement. So again, we're going to pause for 2 minutes. Okay, for a of 3, we should have gotten 5,126.591 gallons to our 3 decimal place rounding. I don't think they told us, well, they told us the nearest gallon, so we'll round that in a second. When we put it into the a of 7, we would want to keep it out a little ways anyway. So if we stub this in now, we should have gotten 4,513.807 gallons. So we can make a summary statement. We can say the max amount of water occurred at t equals 3 hours and was, we want to go to the nearest gallon, so we got 5,127 gallons. Okay, so again, you'll see one of these for sure on the AP exam. They're tricky questions, but when you see enough of them, they kind of become all very similar. Okay, so by the time you sit for your AP exam, hopefully you'll feel confident with these questions. Any time left in the period, you can use to work on your packet that is due tomorrow.